Okay, so let's talk about online learning. So this is online learning is sort of it's really a general and fairly stylized family of models um, family of models for making a sequence of decisions. And really for making a sequence of decisions in settings where the future behavior of the system you're dealing with is uncertain and could depend on your decisions, your actions in weird and unpredictable ways. Okay, so one example to think about is it's a little bit of a silly example, but it's a useful one to keep in mind. Is let's say I'm going to pick stocks. So suppose I've got I need to pick among some set of K stocks to invest in. And each day, I'm going to invest in a single stock. And at the end of the day, I will learn how well the stock I invested in did. And I'll also learn how well the stocks, all the other stocks would have done had I invested in them. So each day I invest in one stock, and then I learn sort of the cost or payoff, if you want to see it more positively, of the cost I would have experienced for each of the stocks. For each stock. Okay. So this is not really a realistic model of investment in the stock market, or not a great one anyway, but it is as I said, a useful example to have in mind to be in this situation where you're choosing among a set of possibilities. You don't really know what's going to happen in the future, but you do have a pretty good picture of past performance for each of the choices you make, and for the choices you would have made at each of the past times. Okay, so abstractly, we can we've got a set of actions, a set of K actions, which we'll just denote with integers 1 through K, and we'll use the shorthand K, bracket K, for the set 1 to K. And there's a decision maker. And the decision maker is making decisions in some environment. This environment is choosing choosing the cost vectors that the decision maker experiences for different actions. And to make our modeling as general as possible, we'll actually think of the environment as adversarial, as some adversary who knows. So the decision maker, we'll call them D. And so the adversary will know D's procedure, know D's algorithm. But if the adversary knows everything, knows D's actions ahead of time, the situation is going to be kind of hopeless. So we're going to allow D to be randomized. Okay, so the adversary knows D's algorithm, but not not D's random coins. Okay, so D is allowed to make random choices, and the adversary won't be able to predict those random choices. So we're going to set up a game between these two players that will proceed for big T rounds. Okay, the rounds are numbered from 1 to T. And in each round, what we're going to do is D is going to choose not quite an action yet, but it's going to choose its distribution on actions. So it's going to choose a distribution P PT, so the distribution for that day. And this is a distribution on actions, and we'll continue using, we've used this notation a little bit, but we'll sort of double down on this. This is the, this notation, this big delta of k, this is the set of probability distributions on 1 to k. Okay, so that's just the same as saying, you know, that the each of these probabilities is between 0 and 1, and they add to 1. So now the adversary is going to choose sees this or knows this distribution, and will now choose a vector of costs for each of the possible actions that the decision maker D could have taken. So we'll think of this as a list of costs, a vector in 0, 1 to the k. So that's a cost between 0 and 1 for each possible action. And sometimes we'll normalize the cost to be between, say, -1 and 1 to allow, you know, negative costs, and that doesn't really matter too much. Okay, and then they sort of execute, you know. So then we choose an action for A, for D is, so the action A sup T is the action for round T. And now D pays a cost, which is the cost of that action, and learns the whole vector C. Now, so these are the two choices they make, and then this part is sort of the execution of the game. One thing to notice is that conditioned on those first two steps, it's often useful to look at the expected cost, and that's indeed what we'll focus on. We will focus on the expected cost. So that's the expectation over an action chosen according to PT of the cost of that action. And if you just sort of work that out, that is actually an inner product of the probability vector, the probability distribution chosen by D, and the cost vector chosen by the adversary. Okay, so in some sense, we're going to sort of abstract away a little bit this part and really focus on this as the cost that the D player is playing. Okay, this expected cost. That's really where we're going to put our thought into minimizing that. Okay, so here's our basic game. Okay, so this goes on for T rounds, and then at the end, the total cost paid by D is the sum over time steps T of these realized costs, what D actually paid. Okay, so this is our basic action, our basic setup, and it's worth asking, like, how do we decide how well the decision maker is doing? So what we're going to be doing is designing algorithms for this setting, and we want to be able to measure how good those algorithms are. So how do we measure? So the first instinct is to try and hope for an algorithm that can somehow guarantee that the total cost it pays over the execution of the algorithm is low. The problem is that's going to be hopeless here. So that makes us sad. And the problem is that the adversary is choosing the costs of all the actions that D is selecting among. And so the adversary could just consistently choose super high costs for all actions. They could assign cost 1 to all possible actions, and then nothing D could do would result in a low cost. Okay, so just looking only at the total cost in isolation isn't very informative, because the adversary can choose high costs for all actions. Okay, so instead what we'd like to do is sort of measure the, how well D is doing relative to some function of the costs that the adversary actually chose in a given execution. C1, C2. Okay, so this is what we'd like to do. We'd like to measure how well the decision maker did, not sort of on an absolute scale, but relative to the costs that the adversary actually chose. And even then, there's a question of like, well, what function of those costs is the benchmark? So each of these are cost vectors, right? Each of these is like a vector of total costs. And so one idea, we could attempt number 1, okay, is to compare to the best sequence of costs. So we look back over the costs, those cost vectors that D observed over the T days of the interaction. And now we can imagine going back and saying, well, maybe on the first day I should have chosen action number 2, on the second day action number 4, on the third day action number 5, on the 7th day action number 1, whatever it is. And maybe what we could hope for is to say, well, the decision maker will do almost as well as that best sequence of making the perfect choice for each day. And again, unfortunately, like that's just not possible. Okay, so this is also hopeless. All right, and it's maybe a little more complicated to see why, but like what the adversary could do is set up an execution where on each day it picks a random action that will have like cost 0, and all the other actions will have cost 1. So for example, if we imagine that the costs as a big table, there could be like a 0 here, and then a 0 here, and then a 0 here, and then on on the last day a 0 over here, and then 1s everywhere else, right? And in this case, in order for the the algorithm to compete well with this, with the best sequence of actions. So the best sequence of actions is like these days where the cost was 0. Sorry, that's hard to read. these days where the cost was 0, the action where the cost was 0 for each day. But if that action was chosen randomly on each day, then like there's no way the decision maker could consistently hit that action. Most days, like k minus 1 out of k days, it would get cost 1. It would end up with very high cost, even though in retrospect there was a sequence of actions with cost 0. So unfortunately, again, like there's just no, this benchmark is too hard to hit, and there's just no reason, there's no algorithm that can possibly achieve it. Okay, so we can't, we don't, it's not enough to just look at total cost in isolation. If we want something relative, we can't compare to the best action, the best sequence of actions in hindsight, because that's too stringent a comparison. That basically, that best sequence, you know, generally will have very, very low cost, but there may be no real way for the algorithm ever to pick that out. Okay, so what we're going to do instead is we're going to look at, we're going to compare not to the best sequence of action, but to the best single action. So in the stock picking example, you know, we make a decision every day, and then at the end of our stock session, you know, our investment session, we look back and we ask, well, which, you know, if I just put all my money in one stock and held that the whole time, and the costs had not changed, what, or had been like exactly the ones I observed, what would I have seen? What would I have paid? Okay, so that's the idea of regret. So let's define the regret on given an execution. The regret of a sequence of actions is, we're going to look at actually the average cost. So this is what's called average regret over time that is actually paid by the algorithm, minus the cost of the best action in retrospect. So with the same cost vectors, but imagining this counterfactual world where I had just chosen one action and held it the whole time. So this is my the realized cost, and this is the cost of A star in hindsight. And I'll compare it to the best such cost. And what's perhaps surprising is that we can find algorithms that have low cost in hindsight. So there exist algorithms, which we'll see, with expected regret, with low expected regret. So in fact, specifically at most 2 square root of log of k over t for every adversary. Okay, so we're going to pause, take a break, and come back, and then we're going to see how we design such an algorithm.